What's up, everybody? Got another video here for you. This one's in the business calculus series lectures. This one is one-sided limits. So we talked about it a little bit in the previous video in the business calculus lectures, the video on limits. We discussed it a little bit, but this is going to be a little more in depth. All right, so one-sided limits. It says if f of x approaches L as x tends towards c from the left, so x is less than c, then we write the limit of f of x as x approaches c from the left. That's what that little minus sign right there is, equals L. This is the notation for it. Likewise, if f of x approaches m as x tends towards c from the right, where x is larger than c, then the limit of f of x as x approaches c from the right, that's what the little plus sign means, equals m. So this is basically right here, this is your notation for the limit as we approach a number from the right and the limit as we approach a number from the left. Okay, so let's work some examples. So we're going to go through, work some limit examples, then we're going to work on the existence of a limit, continuity, and then the last example, I'm going to do another limit example. You might want to watch it, it's pretty good. All right, so evaluate the one-sided limit. So this is equal to the limit of f of x as x approaches 2 from the left. Now we're coming in from the left-hand side. All right, so if you can look at the 2 on the number line, but coming in from the left, that's coming in from this side, from values less than 2. So which of these functions falls into that? Well, if you look, this is x is less than 2. So these are values less than 2 that we're plugging into this function. If you have a value less than 2 that you're plugging into the function, you use this function here. And so this would be the limit as x approaches 2 from the left of 1 minus x squared. Okay, and so we're going to get 1 minus 2 squared, which is 1 minus 4, which equals negative 3. Okay. All right, and keep in mind that when you square this, it's not plus 4. It's not 1 plus 4. It's 1 minus 4. Because, look, that squared right here is on the 2. It's not on that minus sign. Okay? All right, and then we want to take the limit as x approaches 2 from the right. So you can see here, these are values coming in that are larger than 2 coming in from the right hand side. So those are values larger than 2. So this is going to be the limit as x approaches 2 from the right of 2x plus 1, which is equal to 2 times 2 plus 1, which is 4 plus 1, which equals 5. And that's your limit there. That's your limit from the left and your limit from the right. All right. All right, let's look at this one. This is the limit as x approaches 4 from the right, and we're going to do the limit as x approaches 4 from the left. It's the same function. We're coming in from the right, coming in from the left. All right. So this one's a little different than the previous problem. If you notice, if we plug the 4 in, we get 2 over 0, which that's undefined. Okay. So what we want to do, we want to see what is this function going to as x approaches 4 from the right hand side. So just look at it this way. Okay, here's the 4. We're coming in from the right hand side. So that means we would be plugging in numbers like 4.1, 4.01, 4.001. Okay, all this right here that I'm writing over here is just kind of what you're doing in your head. Okay, So think of it this way. If I plug 4.1 into this function, okay, well, 4.1 minus 2 is 2.1. 4.01 minus 2 is 2.01. And 4.001 is 2.001. So it would be safe to say that as I'm getting closer and closer to 4 from the right-hand side, my numerator is pretty much going to be a 2. You agree with that? It's pretty much going to be 2. I know it's not exactly 2, but we can say, it's there. It's 2 pretty much. So if we plug 4.1 in, we're going to get something like 2 over 0.1. See, 4.1 minus 4 is 0.1, and I know this is 2.1, but let's just say it's 2. It's not going to make that big much. It's not going to make any difference. And if we plug the 4.01 in, that's pretty much going to be 2 over 0.01. And then if we plug in the 4.001, we pretty much get 2 over 0.001. Okay? All right. So this right here is the point that I'm trying to make. So what is 2 over 0.1? That's what? That's 20. 2 over 0.01 is 200, and 2 over 0.001 is 2,000. Now, what do you think would happen if I did 4.0001? Well, we would have what? 2 over 0.0001, which that would be 20,000, and so on. So can you see what this is doing? The closer we get to 4 from the right-hand side, the fraction is just getting larger and larger and larger and larger, because the numerator's pretty much staying, it's a constant number. It's pretty much right there at 2, but that denominator's getting smaller and smaller and smaller, so that's making the whole fraction getting larger and larger. So as I'm getting closer and closer to 4 from the right-hand side, well, the whole fraction, well, what is it doing? It's going to infinity. Okay? Now, the same thing here. Look, if I have a number line, I've got a 4 here. I'm coming in from the left-hand side. So I'm plugging in numbers like 3.9, 3.99, 3.999. And hopefully you can see this is going to do pretty much the same thing. 3.9 minus 2 is what? 1.9. 3.99 minus 2 is 1.99. So the same thing there. We can pretty much say the numerator is going to be right there at 2. Well, 3.9 minus 4 is negative 0.1. 3.99 minus 4 is what? Negative 0.01. And then 3.999 minus 2 is minus 4 is negative 0.001. All right. So what are we getting here? Well, it's the same thing as up here, but what? It's negative. Okay? And so you can see this, the closer we get to 4 from the left-hand side, that whole fraction is going to what? Negative infinity. All right? So I hope all that made sense. Okay? And that's pretty much your one-sided limits there. Okay? All right. Now, let me see. I might have it as an example here. Yeah. Well, no. But let me show you this real quick. Let's just kind of throw in an example 4 here. So if I do the limit as x approaches, say, 1 from the right of, say, 2x plus 1, well, how would I do that? Well, this is a polynomial, okay? It's just a linear function here. And so for this, we can actually just plug the 1 in. And that would give us 3 plus 1, which equals 4. So if you have a polynomial or a rational function, and it's continuous at that point, at the x value that you're approaching, if it's continuous there, just plug the number in for x. Okay. All right, let's look at this. Existence of a limit. The two-sided limit, the limit as x approaches, let's just use some random number 2. You can use whatever number you want, it doesn't matter. The limit of f of x as x approaches 2 exists if and only if the two one-sided limits exist. This limit and this limit, so the limit from the left and the limit from the right have to exist, and they have to be equal. So if the limit from the left and the limit from the right are the same, then that's the limit of your function, f of x as x approaches 2. Okay? All right. So let's look and see where that comes in handy. Well, determine whether the limit of f of x as x approaches 1 exists, where f of x is equal to this. So what we have to do here is we have to find the limit from the left and we have to find the limit from the right, and we've got to see if they're equal to each other. So the limit as x approaches 1 from the left of f of x, okay? Because remember what this said. It says the limit of f of x from the left and from the right have to be the same in order for this limit here to exist. Okay, so we're going to find the limit from the left, the limit from the right. They have to exist and be the same. So this is the limit as x approaches 1 from the left. Now we're coming in from the left, so these are the values x less than 1. That's this one. That's x plus 1, which is equal. Now we just plug it in. That's 1 plus 1, which is equal to 2. And then we need to do the limit as x approaches 1 from the right of f of x. So that's going to be the limit as x approaches 1 from the right. Now we're coming in from the right, so that's values greater than 2. So that's this one. That's negative x squared plus 4x minus 1 is equal to negative 1 squared plus 4 times 1 minus 1. And so this is going to be negative 1 plus 4 minus 1, which that's equal to 2 also. So the limit as x approaches 1 of f of x is equal to 2. Okay, because see, you see here, the limit from the left and the limit from the right were the same. Okay, now, I know what you might be thinking here. You might be looking at this part, right? Well, in particular, not exactly the whole thing, but this little piece right here. And you might be wondering, well, how come that isn't positive 1? Because if you square something, it's positive, right? Well, that's right. If you square something, it's positive. But remember, this is negative 1 squared. That equals negative 1. Negative 1 squared is equal to positive 1. You see, this 2 right here is just on the 1. It's not on that negative sign. Okay, so be careful with that. See, this is x squared. It's not negative x squared. See, this would be different. That's different than that. Okay? So remember that. You learn that in algebra. Okay? All right. Let's look at continuity. So a function f is continuous at c if all three of these conditions are satisfied. So f of c is defined, so that means we need to be able to plug the number into the function, and it's defined. The limit of f of x as x approaches c exists, and this limit, whatever we get for this limit, has to equal whatever we get when we plug the number into the function. So basically, steps 1 and 2, if you get numbers there, steps 1 and 2 have to be the same. And then, of course, if f of x is not continuous at c, it is said to have a discontinuity there. Okay. Now, let me just kind of show you some of these discontinuities here just by, looking at a graph. So here's an example. Here's one example of a discontinuity. So for this, you might have a hole in the graph. That means whatever value this is, C, that means it's not continuous there. Here's another one. We could have a graph like this. Okay. So you can see in the first one, the function. See, if this is f of x, then for this one, f of x is undefined. Okay, because you see there's no y value there at C. So for this one, this is discontinuous at C. Okay, so the function is defined because it's defined at whatever this value here is. Okay, there's a y value there, so it's defined there. And the limit exists. It has a limit. But notice the limit. So the limit as x approaches C of f of x, in this case, does not equal f of C. Because, see, this would be your limit, whatever that y value is, and this would be f of C, whatever that y value is, and you can see they're not the same, so that would make it not continuous. And then we have these are infinite discontinuities here. So if you have some value C here, and you have a function that does this, you can see they're both approaching infinity, but that means what? That means that limit doesn't exist. It's going to infinity. Okay, so that's some examples of some discontinuities. There's more, but I'm not going to draw them all. You get the idea. You get the idea of what we're doing here. All right, here it says, show that the polynomial p of x is continuous at x equal 1. Okay, well, to show that something's continuous, we have to show that all of these are satisfied. So we need to be able to plug the number 1 into our polynomial. So we have p of 1, okay, is equal to 3 times 1 cubed minus 1 plus 5, which is 3 minus 1 plus 5. Plus 5, so 3 minus 1 is 2, plus 5 equals 7. Okay, so the function's defined there. And then we have to show that the limit exists. So the limit as x approaches 1 of p of x, which is 3x cubed minus x plus 5. Let me draw that 3 a little bit better. That's equal to 3 times 1 cubed minus 1 plus 5, and that equals 7 also. Okay, so the function's defined, that's step 1. The limit exists, that's step 2. So what we've shown so far is we've shown 1 and 2. And now for 3, well, what does it say? Well, we can see here that the limit as x approaches 1 of 3x cubed minus x plus 5 is equal to 7, which is equal to p of 1. See, they're both equal to 7, so that means that polynomial is continuous at x equal 1. And then here, show that the rational function f of x is equal to x plus 1 over x minus 2 is continuous at x equal 3. Same thing. Okay, so we have f of 3 is equal to 3 plus 1 over 3 minus 2, which that's 4 over 1, which equals 4. And then we have the limit as x approaches 3 of f of x, which is x plus 1 over x minus 2. So that's going to be 3 plus 1 over 3 minus 2, which is 4 over 1, which equals 4. So the function's defined there. That's the first one that we satisfied. And then the second one, the limit exists. And then the third one, the limit as x approaches 3 of x plus 1 over x minus 2 is equal to 4, which is also equal to f of 3. So they're both equal. See, they both equal 4. And so it's continuous at 3. Okay. All right, so here they want us to discuss the continuity of each of these. All right, so for this one, let's just start going through and showing that let's basically show that it's discontinuous at some value. Okay, and we all know here that f of x equal 1 over x. We know the denominator can't be 0. So if we evaluate this at 0, we get 1 over 0 is what? Undefined, right? And so we can stop there. We don't have to go through and show anything else because the first one was not satisfied. So that means it's not continuous there. Okay? And now let me ask you this. Is there anything else? Is there anything else that would make 1 over x undefined or anything like that? No, we can plug in any other number for x. Okay? So, you've got f of x is equal to 1 over x is defined everywhere except x equals 0 because it's undefined there. So it's continuous. It's continuous for all x that's not equal 0. So it's continuous for all x not equal to 0. And that's what they're talking about when they say discuss the continuity of this thing. Okay? Well, what about this one? What about this one? Well, let's evaluate it at -1. That's what? -1 squared minus 1 over -1 plus 1. That's 0 over 0. That's undefined, right? So we know right off the bat, this thing is not continuous at -1. Okay? So we can say f of x is continuous for all x not equal to -1. It doesn't matter what the numerator can be anything. The numerator can be 0. It's just that denominator can't. Okay. All right. So what about this one? Here we have a piecewise function. I'm going to guess that probably what we need to check is it continuous at 1 where it splits there. And see here where it changes functions at 1. All right. So first thing we need to do is we need to evaluate f of 1. Well, does that exist? Well, which function do we use to plug the 1 into? Well, here it's greater than or equal to. So remember, we're going to equal 1 when we're evaluating the function. So that's going to be 2 minus 1 is 1. All right, so the first condition is satisfied. Now we have to see if the limit exists. We need to find the limit as x approaches 1 of f of x. So how do we do that? Well, you know how to do that. We did it earlier. Remember, we have to show that the limit from the left and the limit from the right are the same. So we come down here. So the limit as x approaches 1 from the left of f of x is equal to the limit as x approaches 1 from the left. Now remember, we're going to use this top one. That's going to be x plus 1. So that's going to be 1 plus 1 equals 2. And then we have the limit as x approaches 1 from the right. So all I'm doing right now is I'm finding the limit as x approaches 1. And in order to do that, I've got to do the limit from the left and the right, and they have to be equal. So that's f of x. So that's going to be the limit as x approaches 1 from the right. Now, which one are we going to use? We're going to use this function on bottom because that's the values greater than 1. So that's going to be 2 minus x, which is 2 minus 1, which equals, look at this and this. The limit from the left and the limit from the right, they're not the same. So that means this limit does not exist. So that means this function is not continuous at 1 because the second condition failed. Okay? So let's look at this, x plus 1. Well, we can plug anything, any number less than 1, we can plug into x plus 1. And any number greater than 1 or equal to 1, we can plug into 2 minus x. There's not going to be any restrictions there. So this f of x is continuous for all x not equal to 1. All right. So that's talking a little bit about discontinuity. Okay. All right. So let's look at this one. It says, for what value of the constant a is the following function continuous for all real x? All right, so how are we going to go about working this? All right, so if we look at this, it's defined at 1 because if we take the 1 and plug it into here, we're going to get an answer. A polynomial is continuous everywhere. Okay, so if we do the limit as x approaches 1 from the left, and we're gonna choose 1 to check it because that's where it's broken apart. This function is at 1. So that's gonna be, let's see, of f of x is equal to the limit as x approaches 1 from the left, and that's gonna be ax plus 5, which is equal to a times 1 plus 5, which is a plus 5. And then the limit as x approaches 1 from the right of f of x is equal to the limit as x approaches 1 from the right of x squared minus 3x plus 4, which is equal to 1 squared minus 3 times 1 plus 4, which that's equal to 2. Okay, so we know that a plus 5 must equal 2. And because remember, the limit from the left, the limit from the right, it has to be the same. And so this tells us that a is equal to -3. Okay. So what do we conclude from here? So f of x is continuous for all x only when a is equal to -3. So that's what a would have to be. And you know, for the limit to exist, a would have to be -3. And then we can also go and show that f of 1, okay, if we remember, the f of 1 has to equal the limit. But if we do f of 1, that's what? 1 squared minus 3 times 1 plus 4, which equals 2. So that it satisfies everything there. Okay, but yeah, that's what you want to know at 3. So you'll do the limit from the left, limit from the right, and you'll have to set those equal to each other. Okay. Continuity on an interval. A function f of x is said to be continuous on an open interval AB if it is continuous at each point x equals c in that interval. Moreover, f is continuous on the closed interval AB. That means the a and b would be included. If it is continuous on the open interval AB, so it's got to be continuous on the open interval, and the limit of f of x as x approaches a from the right is equal to f of a, and the limit of f of x as x approaches b from the left is equal to f of b. So that means it's got to be continuous from the right and the left of a, from the right of a and the left of b. All right, so let's talk about this function. Discuss the continuity of the function. And I did not write all the problem down. Discuss the continuity of the function that on the open interval -2 to x to 3 and the closed interval -2 less than or equal to x less than or equal to 3. Okay. All right. So let's look at this. Let's talk about the open interval. Okay. So the open interval, well, I guess before we do that, we can say here that f of x, let me change pen color. So we can say f of x, okay, is continuous for all x values, for all x, except where? Except at x equal 3, because that would give you a 0 in the denominator. But everywhere else is continuous. Okay? So that would mean it's continuous on the open interval. Okay? It's continuous on the open interval because the 3's not included. Okay? But it's not continuous on the closed interval. Okay? It's not continuous on the closed interval -2 less than or equal to x less than or equal to 3. Okay? Now, what I want to do here is I want to show you just a little more detail on this one so you can understand this part of it. Okay? So if you look at this, notice, okay, so we agree that it's continuous on the open interval -2 to 3. Because, I mean, it's saying it's, this function is continuous everywhere except for at 3. We know that. Okay, but let's look and see how this relates to it, to the closed interval. So we know it's continuous on the open interval, but for the closed interval, we've got to show that the limit of f of x as x approaches a from the right. Okay, so let's just kind of let me erase this so I can come up here and write it up here. Okay, so that means it's the limit as x approaches 3. No, I'm sorry, not 3. The end point, let me write it up here, -2 less than or equal to x less than or equal to 3. So this is like your A and this is like your B. Okay, and so this limit here, as we approach -2 from the right, well, that's what is that going to equal? Well, we can just plug the -2 in. So that's -2 plus 2 over -2 minus 3, which is 0 over -5, which equals 0. Okay, that's the limit as x approaches -2 from the right. Okay, and what does it say? That this limit has to equal when we just plug the number in. And you can see if we evaluate f of -2, that's -2 plus 2 over -2 minus 3, which is 0 over -5, which is 0. And you can see those are the same. And then for the endpoint 3, if we do the limit as x approaches 3 from the left of x plus 2 over x minus 3. So we're coming into 3 from the left-hand side. So this goes back, let's erase this. This goes back to what we did earlier. So if we have this, we've got 3, we're coming in from the left, okay? So remember, that's like 2.9, 2.99, 2.999, and so on. So basically, if we plug in the 2.9, the 2.99, and so on, we're going to have some number. Well, 2.9 plus 2 is 4.9, which is basically 5. And then this is going to be negative 0.1, 5 over negative 0.01, 5 over negative 0.001, and so on. So we can see this is going to negative infinity. That limit doesn't exist. So this one right here, you can see it doesn't meet that requirement. So that's where we can say it's not continuous on the closed interval because it's not continuous at 3. All right. And then we have, this is the last thing we go over, the intermediate value property. I'm not going to get into it a whole lot. I'll kind of explain one thing that it's used for. And then we have one more limit example to work that you might want to watch. So if f of x is continuous on the interval a to b, and L is a number between f of A and f of B, then f of C equals L for some number C between A and B. All right. So let's just kind of put it in the terms of, if you have a number here, A, and a number here, and they have y values up here, and they have a y value down here, and then there's some number, some y value in between these two, f of A and f of B, then what it's saying is there's a number between A and B, C, that you can plug in to get that L. So I guess another way, let's say there's a kid, and let's say they weigh 7 pounds at birth. Okay, and then they weigh, I don't know, 100 pounds at 12 years old. Okay. Then we know there's some age in here where they weighed 50 pounds. There's some age between birth and 12 years old that they weighed 50 pounds. That's kind of how you're looking at that. And this is where this can come in handy. It says, show that the equation x squared minus x minus 1 equals 1 over x plus 1 has a solution between 1 and 2. Okay? We want to show that there's a solution between there. All right, so how are we going to do that? Well, the first thing we're going to do is we're going to take the x squared minus x minus 1 equals 1 over x plus 1, and we're going to move that over. So that's x squared minus x minus 1 minus 1 over x plus 1 equals 0. So what I'm going to do is I'm going to take this function here, x squared minus x minus 1 minus 1 over x plus 1. That's my function. I want to show that there's a number I can plug in for x so that I get 0 as an answer. Isn't that what that means? That there's a solution, that this function, I mean, if they're equal and I move this over, then that means they have to equal 0. And so how can I do that? Well, let me show you this. So let's suppose that we have some function here. Okay, and here's the number 1. Here's 1 on the x-axis, and there's 2. Now, this graph here, I have no idea if that's the graph of this function or not. Okay, I have no idea at all. I would have to graph it on some graphing software or take probably another 30 minutes to figure out how to graph this thing. But let's just say we have this graph here. And what we're wanting to do is we're wanting to say that there is some number c in here where you see the y value. Well, I'm sorry, not that. Let me undo that. There's some y value here, and there's some y value here. Okay? And what I'm doing is I'm saying that there's a y value of 0, and I can take some number x, plug it into the function, and that will give me a y value of 0. So how can I show that? Well, look at this. Wouldn't you say in order for this graph to cross the x-axis, okay, in order for that graph to cross the x-axis, that one of these values would have to be a positive y value and one of them would have to be a negative y value, right? Because if one's positive and one's negative, then that means the only way that I can get from here to here is I have to cross the x-axis. And so that's what we're going to do. We're going to do f of 1 is 1 squared minus 1 minus 1 minus 1 over 1 plus 1. All right, and when we plug that in, we get negative 3/2. And it doesn't matter the first one if it's positive or negative. Basically, all we have to do is we need to evaluate this function at these two values here and show that one's positive, one's negative. And so then if I do f of 2, that's 2 squared minus 2 minus 1 minus 1 over 2 plus 1. And that is equal to 2/3. So you can see there we just showed it. We showed that one's positive, one's negative, and so that means somewhere in between 1 and 2 there has to be a 0. All right. All right, so let's look at this one. Find this limit. So if you remember what we talked about in the last video, we said, well, we can just plug the numbers in. But remember what I told you. Now, if you're taking notes and writing all this down with me, don't write this down just yet. 3 plus 1 minus 2 over 3 minus 3. This is 4. Square root of 4 is 2. 2 minus 2 over 0 is 0 over 0. So remember what I told you. If you plug the numbers in, if you get 0 over 0, do something else. Okay? And we worked a problem similar to this in the last video. So if you watched the last video, you probably already know what we need to do. And what we're going to do is we're going to rationalize the numerator. And I'll go over this real quick one more time. If you remember in algebra, when you had to rationalize denominator, you would multiply by the conjugate of the denominator, right? And remember, well, this would be 4 plus 2 square root of 3 when we distribute the 2. And then this one, remember, this is in the form a minus b times a plus b, which is a squared minus b squared. So this would be 2 squared, right? 2 squared minus square root of 3 squared, which would be 4 plus 2 square root of 3 over 4 minus 3, and so on, okay? So that's exactly what we're going to do here. We're going to multiply by the conjugate of the numerator. All right. All right. So let's see what we've got here. All right. So when we do this, we're going to get the limit as x approaches 3 from the right. So remember, this is going to be square root of x plus 1 squared minus 2 squared, a minus b times a plus b, which is a squared minus b squared, over, now this one, don't multiply it out. This is square root of x plus 1 plus 2. Just write them as multiplied together. And so this is going to be the limit as x goes to 3 from the right of x plus 1 minus 4. Right? Square root of x plus 1 squared is x plus 1. 2 squared is 4. And that's going to be x minus 3 times square root of x plus 1 plus 2. And so this is going to be the limit as x goes to 3 from the right of x minus 3 over x minus 3 times square root of x plus 1 plus 2. And look at that. You see there how the x minus 3's cancel? And so that's going to be the limit as x goes to 3 from the right of 1 over square root x plus 1 plus 2. And now we can just plug the 3 in. And so that's going to be 1 over square root of 3. Let me write that 3 a little better. 3 plus 1 plus 2, which is 1 over, that's 3 plus 1 is 4. Square root of 4 is 2 plus 2, which is 1/4. And there's your limit. All right. So kind of a long video, but hopefully it helped. So check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.